All right, so next we are going to go over some of the more traditional graphs that I mentioned. So to start, pie charts. So pie charts are excellent for nominal data. Pie charts, as long as you don't have too many categories for your nominal data, in which case it just gets hard to summarize anyway, because clumping, I mean, you could conceptually clump some of these, right? If you have favorite subject data, you could put science together with math and call it STEM. You could put like English history, um, and you could put just English and history together and then look at art and music as phys ed as electives, or you could do it more like a college and put art in with English and history and music in with English and history. It's what I'm saying is it's swampy. So if you've got a limited number of categories, or you can find a logical way to reduce the categories and clump them, so like nominal binning, then you can use a pie chart and it's perfect. Pie charts need to be clearly labeled. You can either label them in the slices or you label them with a key. Labeling in the slices, if you've got space, is often better because it means people don't have to look back and forth between a pie slice where they're getting the size of the group, kind of a proportionate size of the group, and a key to figure out what the group is. So we often label right in the pie slices or just outside of them. And along with saying what the category is, we might do the frequency or a percentage. So percentages are relative frequency times 100. So we basically would have either frequency or a version of relative frequency in that table. Um, for ordinal and discrete numerical data, pie charts are okay, but and the reason that they're kind of is because they don't do like order is not important in a pie chart. They're great for nominal data because order is not important in a pie chart and order doesn't exist in nominal data. But with ordinal data, we could get more information. Yes, we can look at this and see that it starts at 0 and then goes to 1 and then 2 and then 3. Like we can see what the values are, and we can get an idea of the spread. We can tell that the slices are getting smaller as we go up here. But for example, it doesn't show in here if you're just taking a quick glance. Like, I wouldn't necessarily notice this 0%, right? And that might not even be labeled. Okay. And then this five, it gets a little hard to see when you've got these little tiny slices. This five should be over here, right? So the pie chart doesn't intuitively show the lowest and highest data values. It also does not show zero frequency values in a meaningful way. So you can use them to show this kind of small range, ordinal or discrete numerical data, but you might not want to. You really don't want to use them for the I was gonna say fancier. It's not fancier. Just the mathier numerical data, the continuous data, or larger ranges of discrete numerical data. You really don't necessarily want to use them for this for most of the same reasons, and because the shared edges between the bins, like it's just not intuitive for a pie chart. So this is acceptable. This is acceptable, but they're not the best way. Bar graphs are kind of the most versatile. So with a bar graph, this is the same as that first pie charts data. Um, this works more or less as well as a pie chart for showing nominal data frequencies. You could argue, I'm going to flip back a few slides. You could argue that this is more easily interpretable in the sense that, like, you can look at this and see that music is the biggest chunk really quickly. And not only that, you can also tell that it's only a little under a quarter of the data. It's maybe like 20% of the data. And you can tell that from the pie slice. You can't get that kind of relative size comparison boiled down to like what percent of the data it might be as easily on a bar graph. But you can still see quickly that music is the highest category, right? So it's giving you most of the information the pie chart does. And you can also, for nominal data, if you remember, Pareto charts are a thing. You could reorder these categories so they went from the lowest favorite math to the highest favorite music in this data set, and that would give you a different type of information about the nominal data you're working with. So bar graphs and nominal data get along great. Bar graphs and ordinal and discrete numerical data also get along great. So if you're working with data like these, this is a more appropriate way to display it than a pie chart because a horizontal axis is the best thing to use when you've got data values that are, linear numeric data values like this. Because it clearly shows where the endpoints are. It clearly shows any gaps. You want to make sure that if you are drawing or interpreting a graph like this, that the data values are in even increments. You shouldn't have skipped bars here. And so if you've got it set up correctly, it shows the overall distribution of the data more clearly than a pie chart does. Okay, so great for this. For continuous numerical data, you can use a bar graph, but it's not the best option. The binning here, where the edges of the bins touch, we actually want to be using a graph that does the same thing because visually that signifies continuity. Okay, so this is better than a pie chart, but still not the best option to work with these data. So, can you draw one? Sure. It's mostly fine. It's not the best. One quick note here. On the last graphs, I had frequency. Here I have relative frequency. Those are both fine. You wouldn't use the cumulative frequency on an axis, but either just frequency or relative frequency are fine. Okay. Whoop, this is not the right label. Please hold while I fix it. One of these days, I'll stop saying things like, please hold, as if you actually also have to wait when I pause the recording. I actually will probably keep doing that. It's a very hard habit to break. Anyway, next graph type is a line graph. So line graphs are the liney form of a bar graph. I will show you what I mean by that in a minute. But basically, the same points that would be the middle of the top of a bar graph, you've got them on your line graph, and then you connect it with a line. This is not acceptable for nominal data. The reason this is not acceptable for nominal data, really, even though it's interpretable, but it's not great. I line connecting one point to the next indicates some kind of continuity between the categories, but there really isn't any form of continuity between these categories. They are clear, distinct categories. So you wouldn't really want to have lines connecting them. It's better to have the distinct bars. This is an acceptable and a good form of graph to use for ordinal and small range discrete data. Um, the reason that this works okay is even though, so these aren't continuous data, right? You can't have like a zero point 0.5 sibling here, but they're conceptually continuous. The ordinal nature of them means that you go from one to the next to the next to the next with a smoothness from category to category, even though they are discrete chunks, discrete categories or numerals. So it's not continuous in like a continuous numeric way, but it's a continuous set of categories. So the line makes a little bit more sense here. Okay, so again, this is just if we had the bar graph for this, it would have a bar up to here for 0, up to here for 1, up to here for 2. That's all we're looking at here. If what we want to emphasize is kind of the shift across the categories and the overall shape of the distribution, this can be a nice way to do it with this type of data. This is an okay version again of a graph for continuous data, but there are just some little tweaks that we can make to it to make this axis make more sense. And we will turn our continuous data into a graph that we call a frequency polygon that basically serves the same purpose, but just works a little better for continuous data. So again, line graphs are best for ordinal and discrete numeric data. They're kind of okay for continuous numerical data, but not the best. They're meh for nominal data. I'm going to, by the way, go back through these and just mention some of the things that you can and cannot tell from some of these different graphs. So notice I didn't even bother with a nominal version of this. We're not going to do that because it doesn't make sense on an axis like this. You can't do it. So a histogram by nature has numeric values along this axis. However, notice that these do not match up with these data values. This is a small range of discrete data. We already have a good number of rows in our frequency table that we can turn into our bar graph. So we don't need to do any binning. But histograms by nature, you label the edges of the bins. You don't label the middle of the bar, you label the edges. So if we want the first bar to mean zero, then and then the next one to mean two, that means the bars are one apart, but zero has to be in the middle of the first bar. So instead of the first bar being labeled as one, its sides are labeled negative one half and positive one half. Instead of the second bar being labeled as or yeah, the well, here, let's go a little further over. Instead of this bar, so instead of this one being labeled just with a three, it's two and a half to three and a half. So it still gets across, like the threes are the only thing in the two and a half to three and a half range. You can make it make sense. But this is just not, why wouldn't you just want to do a clearly labeled bar graph, right? So this is for ordinal and discrete numeric data and really wouldn't make sense for nominal data at all. However, for continuous numerical data or large ranges of discrete values, this is where it's at. So here we make good use of these weird shared edge bins because that's what we're labeling the edges of the bars with. The bars are connected because 45 is right there. We're just saying from 40 up to 45, that's this one. From 45 up to 50, that's this one. Okay? So these bins finally make sense directly on a graph here using the edges of them as the labels instead of the ranges as like the label in the middle of the bar like we were before. Also, these data are continuous, so the bars being connected and giving that visual continuity is the way to do this that makes the most sense visually and conceptually. In the same way that histograms are best for continuous numerical data over bar graphs, frequency polygons are best for continuous numerical data over line graphs. So these, the labeling is a little weird again, because if you remember for a line graph, I said that you're just putting a point at the middle of where the bar would be. Same thing on this, but you're using a histogram. So the middle of the bar on the histogram is going to be the middle of this bin. So the middle of this first bin, 45 to 40, if I do 45 minus 40 and divide by 2, that gives me 2.5. So 2.5 between there, 42.5, right? So 42.5 here, 47.5 would be the middle of this bin. Note that this also goes back one. So we don't actually have a 35 to 40 listed, but we do have a 37.5 value. It's just we put the point down at 0 because there is nobody in that group. We go one lower than and one higher than the groups listed in the frequency table in order to complete our frequency polygon. Polygon means a closed shape. So going all the way down to the zeros on the ends instead of just stopping at the lowest and highest value like we do on the line graph is what gives it that name frequency polygon. It's giving you the overall shape of the distribution as a closed shape on the graph because it closes with the axis. So going back to these pie charts, what you can find out from them depends on how they're labeled. If your pie chart is labeled like this with raw numbers, then you can do, some basic calculations off stuff. Say you had, for example, the number of siblings and then it was labeled with the frequencies instead of the percentages. You could actually do calculations directly off that pie chart if it was clearly labeled. Okay? You cannot do clear calculations from categories in continuous data in the same way. So if I wanted, for example, to figure out the average of these data, and we'll get to calculating averages later, but I would need to know exactly how many people have exactly how many value. I would do the data value times the number of people who had it, 0 times 15, and then 1 times, let's see if these are all whole numbers. This is a little past the middle of this, making it 23. Even if I didn't have this, I could still figure out all of the exact data pieces if I put a little work into it, right? I could calculate specific things off of that. Once we get to bins, you can't get that precise in your calculations anymore. Even if this was labeled with frequency instead of relative frequency, because we don't know what the actual values are for the 35 people here. Okay, you might have a whole bunch of people who are you might have like 34 people who are at 44 point something, and then just one person down at 40. You might have people across the full spread. We don't know. We just know there's a bin. So binning gets rid of the specificity of your data in a way that means you can only make estimations and not do more specific calculations like you would be able to here. And the same thing is true if you're looking at a line graph or a histogram or a frequency polygon. The thing that you want to, well, really, if you're looking at a line graph, the same thing is true. If you're looking at a histogram, the only way you can do precise calculations off of them is if you know that it's whole number data and you have bins like this. But again, here, these are real bins where it's actually continuous data, and it's covering more than one possible data value. So here you can only make estimations. Okay. So quick summary. Pie charts and bar graphs are great for nominal data. Those are going to be the best ones. You can make arguments for either as being better depending on what you're trying to emphasize. Bar graphs and line graphs are the best for discrete data. You've got both of these overlaid here. So a bar graph is just or a line graph rather is just the connected tops of the bars of a bar graph. Those are good for discrete data because the separation on the bars and the specific values for the labeling of the line graphs tells you that it is discrete and you've got specific numbers in there. Histograms and frequency polygons, again, same general idea as far as overlaying them. But typically, because you're working with bins, any calculations you can do off of them are less precise because you don't know what the actual data values are. Okay, so those are the univariate frequency graphs. Now, we're almost done with this chunk, but I'm going to go briefly over some bivariate and multivariate graphs. So uni means one, bi means two. Univariate graphs, the ones we just went over, provide a visual descriptive summary of just one variable. Bivariate, two variables. Multivariate, three variables. So some examples of bivariate graphs. The one that's covered in this section of the book is a time series graph, and we'll talk about those in a minute. But I'm also going to talk briefly about some of the other graphs we'll run across later on. So a clustered frequency bar graph. You can have a bar graph with two or more sets of bars on it, still just showing frequency, that shows multiple variables at once. You can also do bar graphs that instead of graphing the frequencies, you graph averages of numerical data. So you can use those to display combinations of categorical and numerical data. And I'm also going to show you scatter plots, which you should be used to. They're those XY things that you used to have to do the algebra graphs on. Yeah, those. Um, and then time series are a specific case of a scatter plot. So clustered bar graphs. Okay, when you have more than one variable that you are trying to work with the frequencies of, it makes sense to list them together sometimes. So what we have here instead of a frequency table is a contingency table. It's one variable contingent on the other variable. What year these folks are in depending on their major, or what major they're in contingent on what year they're in. So we'll come back to this kind of frequency table, this kind of multivariable frequency table or contingency table when we do chi-square tests later in the semester. When you have data that makes sense to display like this, it very often also makes sense to display them in a clustered bar graph. So you can see here that the freshmen are all clumped right here. The sophomores are all clumped right here, juniors here, and seniors here. And then depending on how darkly shaded the bar is, that tells you what they said that their majors were. So you can see that the number of undeclared majors is very high for the freshmen and then goes down from year to year. For humanities and STEM, it starts pretty low. You get more folks declaring into STEM earlier on, and then more folks going into humanities as you get into the higher grades, although STEM continues to increase as well. So you can use these to do some specific calculations. If you didn't have this contingency table, you could again figure out pretty accurately, like these are both kind of in the middle, but this is a little lower. So this would probably be 12 and 13, or sorry, not 12 and 13. This one's a little hard to see because it spans of 10. It would probably be like 14, 15, 14, 16. But if you had a table that, a graph that had more divisions on the axis, you could get some specific calculations out of it in terms of frequencies. So, clustered bar graph of frequencies. Again, one of your variables ends up going into a key, and you indicate which bars are which based on color or shading, and then you cluster the bars by the other variable. We'll come back to those with chi-square tests, like I said. If you are working with one categorical and one numerical variable, so you can kind of get past frequencies, you might calculate averages. So here we've got another kind of bar graph that is showing the average GPA for the students in the different majors. So on the x-axis, you have a categorical variable. And on the y-axis, you have your numerical variable or numerical-ish calculated variable. And so when you have something like that, a bar graph is great for showing that information. It's easiest to first calculate the averages, which again, we'll get to that in a couple sections, and then just put it in a little table like this to graph it. We will use these when we're showing results from t-tests and ANOVAs. Scatter plots I mentioned are those XY plots. So these are used when you've got more than one variable that acts like a continuous numerical variable, or sometimes with larger ranges of ordinal variables. And unlike on the other graphs, every individual person's data is shown here. So we could, if we had the full list, which I didn't give the full list, we could probably figure out which participant ID the person right here had by looking and seeing who had the lowest reported weekday sleep, which looks like it's about 4.5. And then daily social media hours around 3. We would be able to identify. Oh, wait, actually, they are right here. That's participant 3, 4.5, and 3. Spot on. So you can identify specific individuals. You often see these graphs with a line of best fit in them. We will use those when we are looking at correlations and also regression analyses at the toward the later end of class. So those are all bivariate graphs. This time series graph that the book talks about is kind of a specific type of bivariate graph where one of the variables is time. And here we can kind of think this as a scatter plot, or we can think of it as a line graph. Um, we can't properly call this a scatter plot because January, February, March, April, those are not numerical units, and scatter plots need numerical units. But it acts the same way as one. It's basically a line graph where as you go across, the readings or the averages or whatever are at even increments. However, time series graphs, because they have those linear horizontal axes, they make the most sense if you're talking about time that advances in a linear order. So, for example, if you're looking at a business's profits and you want to look at how their profit margins grew from quarter to quarter, from the first quarter they were open over time. Okay, if that's the case, then this kind of graph is perfect. This average temperatures thing this isn't really the best way to do this one because average temperature by month, I mean, for this, it's just 2025, but we could show like averages over multiple years and we could put it in a circular chart called a radar chart that would actually show you where December and January meet back up because a lot of time is cyclical. If we're talking about time on a clock, like a 12-hour clock or a 24-hour clock, or if we're talking about months of the year or anything like that, sometime is cyclical. So time series graphs can be used with time, even if it is cyclical. But basically, I want you always thinking about what the little parts of the graphs mean. A linear axis like this that goes from a lowest to highest or has ordered stuff on it, like we're supposed to be paying attention to that. And so if we're working with data that are not actually linear, it might not be the best kind of chart to use. All right. So this is, again, technically bivariate. It was included with all the other univariate ones in the section because the only thing we're really interested in is the degrees, right? The specific thing we're measuring on the y-axis. And then months are just like the spans, like the distances between measurement points, but it's equal, so it's not exciting. But technically time is a variable, so this is bivariate. Okay, you can, with not just these, but all sorts of different graphs, you can put multiple series on a single graph. So if you have more than two variables, then you can call it a multivariate graph. And it's very common to include multiple variables on a single graph in order to make different visual comparisons of values. So that is where we'll end now for charts and graphs. Again, we will come back to how to use specific types of charts and graphs to help display results when we get to inferential testing. But for now, this is where I leave you.